Wow, okay. All right, well, my name's Tim White. I'm a geologist at Penn State, and I've actually spent most of my career doing underwater research. And only in the last 5 or 8 years have I come on land and begun to think about the critical zone, which is what I'm going to talk to you about today. I have a lot to say, and I also have an activity that I'd like to walk you through. And so, Dan, I'll be honest with everybody, and I suspect that I may not get everything done tonight,
Okay.
and so you might have to listen to me a second time.
Oh, that'd be great. Yeah, no worries.
So for today, what I'd at least like to get you through is a basic understanding of what critical zone science is, and also what critical zone observatories are. And I will also say, I don't know how you guys want to deal with this, but I will take questions at any time. You don't hesitate to ask for clarity anytime. Okay, so the format for this lecture is as follows. I'm going to begin with a definition of the critical zone and then talk to you a little bit about what critical zone science is. And then importantly, I'm going to tell you about, a little bit about the history and development of the science. And I think if there's, there'll be several important points I'd like to leave you with, but one of them is right now, and why I'm going to tell you about the history and development of this science. And the reason I'm going to tell you about it is that the history of critical zone science is ongoing. It's a very new realm of science, and it's literally evolving. I mean, it's a little bit over to say as we speak, but this is a science that's evolving each day. New things are happening, new people are becoming engaged in it, and so it's a very exciting time for people who study the Earth's surface from a variety of different disciplines. Then, if I can get through all that, I'll talk to you a lot about why this is relevant to society and what humanity's role is in impacting the critical zone. What I don't think I'll be able to get to this evening is some of the specifics of the science that we're doing. I do want to get to tell you a little bit about opportunities that you may want to consider as primary and secondary educators. So we'll see where we go, but I might skip through some of this and jump down to opportunities depending on what time it is. Oops. All right, so the critical zone is a term that was published first in 2001 by our U.S. National Research Council. The National Research Council is an organization that oversees all science, basic science strategy in the United States. And so they gather panels of renowned scientists every 5 years, and they group up in disciplines. For example, up there it says the 2001 BROS report. BROS means Basic Research Opportunities in Earth Sciences. And so they had a group of panelists who were earth scientists, and they strategized on what we as a nation should be thinking about in the coming 5 years. This was in 2001. And they coined this term critical zone. And they didn't exactly define it. We've since been batting around a definition of it. The one you see here is my definition of it. And it refers to the very thin veneer of Earth's surface. And I should be clear that we're talking about the continents now, not the oceans. So it's the very uppermost part of the continents that spans from the top of vegetation, however high that may be, down through soil and into whatever subsurface depths fresh groundwater exists and circulates. Before I go on to help bring some clarity to that definition, let me also say that there's some debate in the community of people who do this kind of work about whether we call this the critical zone in capital letters like I show there, or critical zones. My personal preference is the capitalized version of it. And if I were to think of critical zones in the plural, they would be things like the North American critical zone, the South American critical zone. The reason I say that is from the shoreline of the Atlantic Ocean to the shoreline of the Pacific Ocean, it's a single critical zone. It varies in thickness and character, but it's the critical zone. It's not a series of zones. It's one zone that spans the entire continent. Okay, so just to think about this definition a little bit more, think back not too long ago, where I said it spans from the top of vegetation, however high that may be, down to whatever depth groundwater exists and circulates. Well, one place to think about that is the tropics. Most of the tropics have extensive forests where it hasn't been logged and very well-developed understory. These forests can have trees that are certainly 100 or a couple hundred feet high. Because it's warmer and wetter in the tropics, the soils that develop there are very thick, and the weathering that goes on down into bedrock below the soil, into what we call regolith, weathered rock, can extend quite deep just because there's more water and warmer temperatures to drive chemical and physical processes. So in a tropical part of the world, the critical zone, the thickness of it, can be very thick. Hundreds of feet of vegetation down through maybe many hundreds of feet of rock, soil and rock that are saturated with fresh water. Now, if you jump to the high latitudes, to one of the poles, in this case, these photos are from the Svalbard archipelago, which is just kind of east of northern Greenland at about 80 degrees north, not far from the North Pole. If you go there and think about the critical zone, well, there aren't trees that we think of. There actually are woody plants, but they stand about an inch high. Most of the vegetation is lichen. The soils, if you look in the bottom right hand there, are virtually non-existent. It's just rocks, boulder fields everywhere. And what groundwater there is mostly permafrost. It's frozen year-round. And so in a place like this, the critical zone might be measured in inches, maybe in the summer in feet. But so the point is, depending on where you are on the planet, the critical zone can be very thick or very thin. But it's still what we call the critical zone, spanning from the top of whatever vegetation there is down to wherever groundwater freely exists and circulates. Is that clear?
Yep.
Any questions so far?
Yes. With what you're saying, so would the desert be a critical zone?
Anywhere on the continents is a critical zone. It's a great question, because you think about the deserts, and maybe in some deserts, at least as deep as you might want to dig, you'd never find any water. But eventually there's some water down there. It might be really deep and only a little bit. But yes, the desert is a critical zone. It's a good question. Any other questions?
Is an
All right.
aquifer in the critical zone, or is that below? Like the Ogallala aquifer in Central North America?
That's a great question also. So what we're talking about is water table aquifers. And I don't know if everyone knows what I mean by that, but there are places in the world, including out west where you're referring to, where there are deep layers of rock that contain fresh water, but are disconnected from the surface by other layers of rock that don't contain fresh water. And so in a setting like that, that aquifer, it's called a confined aquifer, is not part of the critical zone. So it's only the part that's the water table, that's the water that's percolating directly down and existing right below our feet, not under any confined conditions. Does that answer your question?
Yes, thanks.
Mystery man off to the out of my view.
I'm Rich, one of the instructors, Rich Neat, sorry.
Oh, okay, it's fine.
Yeah.
These are great questions. Great questions. Okay, so soil is a very important part of the critical zone, and many people who work in the critical zone focus their work on soils. But soils are just part of the critical zone. I like to think of them as being at the heart of the critical zone. They're at the place that overlaps, as you'll see in a minute, between four, what I like to call spheres. And so if you see this figure that I just popped up there, soil crit zone, it's something I'll come back to a little later in this talk. It was a project that was funded by the European Union. But what that image is meant to convey is that the critical zone exists at the interlap between four spheres. The yellow one up at the top, I think of as the atmosphere. The brown one at the bottom is the lithosphere, or rock. The blue one on the left is the hydrosphere, or all the fresh water and ice that's on the planet. And then the green one on the right is the biosphere, all living things. And so they put soil in that title, soil crit zone, because soil exists right at the heart of all that. Soil forms by the interplay between the atmosphere, the biosphere, the lithosphere, and the hydrosphere. And we'll come back to that again later in this talk. Any questions so far? So, critical zone science, and then this whole concept of observatories, which I'll describe to you in a bit, but there are our research sites and the facilities that exist at these sites. This science, it evolved from the recognition that many diverse groups of Earth's surface scientists, including ecologists, geologists, soil scientists, hydrologists, engineers, and on and on and on, were asking questions that were similar, but they weren't interacting with each other. So all these brilliant people focused in their discipline, asking questions, but without availing of and collaborating with other people with other expertise who might help them understand the questions they were trying to answer. And so after a while, some people began to recognize that, hey, we're all asking the same questions. Why don't we work together? So for example, there was a group of hydrologists that formed what's called the Water Environmental Research Systems Network. And they were asking a series of questions that you can see here. What's going to happen to the water cycle as the human population grows and climate changes? What's going to happen? Are we going to have enough water? Is there going to be enough available for us not just to survive, but to continue to have a high quality of life, to continue to drive our industry and our economy and so on? And furthermore, are there ways that we can predict and better manage our water so that we can deal with things like changing use of water and changing climate and the impacts it might have on water resources? Oops, I keep going the wrong way. A group of what are mostly ecologists, but lumped under the term geobiologists, began to ask questions about how do living organisms interact with soil and rock to literally sculpt the landscapes where we live? Do they play a role in forming topography? How might changes in climate affect the way life interacts with the critical zone? And furthermore, how might humans, as part of life on Earth, how might what we do to the landscape impact the critical zone and the way natural processes occur? And then finally, and these are just a couple different examples, but finally, among the community of people called geomorphologists, these are people who study the landscape and how it got to be the way it is. But they were asking questions like, what controls the land surface? How does it form? What controls the depth of soil and the thickness of soil? What role do plants and animals play in sculpting the landscape? And how does that lead to the development of the critical zone? So I've just kind of hinted here at 3 different communities and the sort of questions that they were asking. And over a period of about a decade and a series of many meetings many of which were funded through tax dollars from our National Science Foundation, getting these disparate groups of scientists together in a room for a day or two, just talking all this stuff out. We came to the agreement that there were basically 4 driving questions at the heart of critical zone science. And if you think back to that little soil crit zone diagram I showed you, you'll see that these questions each revolve around one of those spheres. And so, for example, the top right-hand question there is, what processes control fluxes of carbon, particulates, and reactive gases over different timescales? So thinking about what's happening in the atmosphere. And then on the bottom right, how do variations in chemical and physical weathering processes impact the critical zone? So thinking about the lithosphere, the rock part and the soil part. And then over how does biochemistry, biogeochemistry, govern sustainability of water and soil resources? So getting at the hydrosphere. And then finally left there, what do processes that nourish ecosystems, so plants and animals, how do those change over human and then longer time scales? So it comes back, even if you look at those questions and you say, gosh, I don't even know some of those words, at least step back and think about that drawing of soil crit zone and just think atmosphere, biosphere, lithosphere, hydrosphere. How all that stuff works together to drive processes on this little area of the planet where we live and what allows us to thrive. Any questions on that? And I see many of you writing madly, which is great. I like people who take notes. But I'll somehow get this to Dan so that you can just have this presentation.
All right, Tim, we're going to share the live binder with them so we can put it right up there for them.
All right. So hopefully you at least have, an introductory understanding of what the critical zone is and sort of what's at the heart of the science behind critical zone science. And I'll get into more detail either this evening or in a second lecture. We have these things called critical zone observatories. And I'll tell you what they are in a minute. But before I do, what I want to tell you a little bit about the history of how we got to where we are. And so this new realm of science, critical zone science, we have begun to succeed in bringing a very diverse, interdisciplinary group of scientists together. This is, you know, I don't know what the equivalent might be for you guys. It might be like, I don't know, so some of you are primary school and some of you are high school teachers. It might be like putting primary, you know, first grade teachers and 12th grade teachers in a room and saying to them, we want you to develop the exact same curriculum. This is very challenging to bring ecologists, geologists, hydrologists into a room to talk about this stuff, because we don't even speak the same language. I know all the words for all the rock types in the world. I can bring the most brilliant ecologist into the room and talk to him, and he or she will have no idea what I'm talking about. And the same with them. They'll tell me all about the plants that they're studying, and my eyes will glaze over. So the first thing we have to do is learn to talk to each other. It's really hard, but we're getting there, and we've begun to address and accomplish some fairly high-level science, dealing with pretty complex interdisciplinary questions. And so how are we doing that? Well, first we had to think about the challenges. One, the critical zone is a very complex system. To understand critical zone processes, this is a global issue. It isn't as if we have a critical zone in North America and there isn't one in Europe and Asia. We're talking about all the continents, so this is global in extent, and therefore, to understand what's going on not only requires international cooperation, but collaborative funding to get at these things. And it's also deeply interdisciplinary. And so we need to develop a completely new set of scientists. So I'm 53 years old. I'm a classically trained field geologist. And I'm doing my part in helping support and move critical zone science forward. But the simple, and I'm a pretty smart guy, so I can sit and talk to an ecologist or a hydrologist and learn to understand them. But the bottom line is, I'm a geologist. I see the world as a geologist. And what we need are people who don't have those blinders, who from a very early age are trained to think across disciplines. And so we're literally trying to develop a new generation of scientists as we're creating this science. So our approach is what we call the network approach. The first thing is to steer around that complexity of the critical zone. What we try to do is look at a site or a process and try to hold as many of those variables of rock and water and plants and animals and the atmosphere, hold as many of those constant as we can, and then study one process within it. And then once we understand that one process, start looking at something that's linked to it. And so start simple and then build out and get more complex. The other part of the network approach that's important is that we need to be able to compare data that's gathered in the exact same way at multiple sites. This is a real big challenge. It may sound easy, but one lab has a device that gives you such and such data by one method, and then the other highfalutin university lab on the other side of the country gets the same data, but from a different device. And that's not always comparable. So you're constantly trying to work out, well, what device did you use? What method did you use? How did you collect your sample? And getting everyone to collect their samples the same way and analyze them the same way is a huge challenge. And then at the bottom there, I mentioned that we're trying to create this community of scientists that's not only trained early in their career to think interdisciplinarily, but also to take the middle-aged and older guys like me and drag us through the process and really create a new community of scientists. Okay, so this network approach, I'm going to focus just for a moment because it might be a little bit simpler to think about, but if you think about soils sitting right at the heart of the critical zone, we know from many decades, soil scientists figured this stuff out in the 1920s and 30s, that soil formation is controlled by 5 natural factors. And those are the parent material, the rock or sediment that the soil, that weathers to form the soil. The climate that it exists in. So obviously you saw those photos of Svalbard up near the North Pole where there's just rock. There's almost no soil because it's frozen all the time. And if you go to the tropics, the rock, because it's warm and wet, the rocks degrade quite rapidly and you get thick soil. So the climate. The topography. If you went to Mount Everest and looked at a really steep slope, well, there's no soil there because gravity doesn't allow it to stay there. It just slides down the mountain. Whereas if you, for example, where you guys are, or in the valleys here where I live in Pennsylvania, we get thick soils developed on the flatlands. Biota. So what are the plants and animals doing? Groundhogs and ants and you name it, burrowing down and mixing the soil. Plants growing their roots down, opening up cavities in the soil that let water percolate down. And then time. So if a piece of rock is sitting out on the landscape for a year, not much is going to happen to it. But if it's there for 1,000 years, a lot's going to happen to it. And then finally, I had there at the bottom, number 6 is humans. And as you may see this evening, but certainly in a second lecture, we play a huge role. Humans are now the dominant earth-moving process on the planet. We move more rock and sediment than all the earthquakes and volcanoes and everything else, rivers combined on the whole planet. Humans move more than all those natural processes combined. Any questions? Do you feel like you're ready to scream yet? Okay, good. If you are, just tell me. Okay, so I'm still talking to you about this network approach because this is at the, this is the basis. It provides the framework for how we go about getting at the complexity of critical zone science. So look, I'll go back here for a second. There's these state factors, and then I've added humans at the bottom. And then over here, you can see that what this is meant to convey is each of those boxes represents a study site. And so what you should think of is that each of those labels there, lithology, is the same as parent material, topography, climate, biology, time. Oops. It's this list right here. And then here it's humans, whereas on this one I say disturbance, but that's us. And so each one of those boxes is meant to say, okay, if we want to understand, let's say, the role of topography, well, we can't just go and set up a study site in central Pennsylvania because it's relatively flat here. So we need to set up a site in Pennsylvania and then in the Rocky Mountains. Or if we want to understand the role of climate, well, again, you can't just do it here in Pennsylvania. We need a site in Puerto Rico and in Alaska, as well as Pennsylvania. So we can have wide variations in climate to understand the full range of possibilities that exist on Earth. And so on for each one of these. Someone asked earlier about a desert, so if we were thinking about climate change, climate gradients, we might also stick a site in the desert. And as you'll see, we have a site in Arizona. I think I'll skip this one. It's just, and I think I'll come back to it later. Okay, so fortunately, the people who have led this effort to organize critical zone science recognized very early on that this was going to require international cooperation, and that we needed to develop a network of not just data sites, but also of people. And so very early on, we were able to obtain funding. I'm not going to go through all these lists, but we were able to obtain funding from a variety of sources: the U.S. National Science Foundation, the European Union, and then an organization called the Worldwide Universities Network that Penn State's a member of. And so you can see here, beginning in about 2003 through about 2006 or 7, we held a series of workshops. Many of them were in the United States, some of them were overseas in Europe. And I guess down there in red, you can see in 2006, we had a big meeting at the University of Delaware, and it was called Frontiers in Critical Zone Science. And this was kind of a big deal. There were probably 150 people from all over the world. And I'm going to, at a couple different points in this lecture, I'm going to point to you to some potential resources. On the left there, you'll see Brantley et al. 2006. It's a short report. It's probably 35 or 40 pages long. It's available for free download at that www.czen.org. I suspect if you're a first grade teacher, this is not something you'll want, but if you're a high school teacher, there's information and imagery in there that you could use. It's a PDF, and I don't know if you guys do PowerPoint, but it might be a useful resource for you to consider. And then another more recent one is this Landscapes on the Edge. It's from the National Research Council. It's the I think it's 2012. It's a very recent report. It only has a short section on the critical zone, I think 8 or 10 pages, but there's some great images in there. So, and it's a free download. So think about looking to those. Another, this is probably a little bit more detailed than most of you would want, but both these last two slides are meant to provide information on the state of critical zone science kind of through this part of the history. The first 5 years of critical zone science, well, these reports and this issue of the journal Elements basically tell you everything you need to know and have really nice images in them. And if you guys can't, if someone's interested in this Elements and you can't get a copy of it, just, Dan, tell me what to do here. Are you the common point between these people and me?
Yes, sir.
Okay, so if you can't get this and you want it, talk to Dan, and Dan will contact me and I'll arrange to get it for you.
Sounds good.
Okay, so a little bit more recent history. We had another big meeting in Washington in 2007, and That meeting, shortly thereafter, the National Science Foundation said, okay, we're buying into this. And they put out a call for proposals, and at the end of this competition, 3 critical zone observatories were chosen for funding. What that means is each one of these sites received $1 million a year for 5 years of funding. So this is a $15 million investment in figuring out critical zone science. At the same time, and we were able to convince NSF that this training people part of this is really important. And so we got some money to support what we call the International Scholars Program. And that program just ended this summer, and it allowed us to send about 55, over those 5.5 years, about 55 US graduate students to, mostly to Europe, but some sites in Asia and Australia, to either work at field sites or work in laboratories in Europe that have facilities that we don't have here in the US. And so at least you'll see towards the end of this that we are now beginning to have some efforts to educate, to have outreach and education to people like you guys, primary and secondary education. But really, because we've been so early in the development of the science, by necessity, we've focused primarily on graduate research, people doing their masters and PhDs. Just a couple comments from some of the PhD students. You know, I'm not going to read all these, but because I was the person doling out this money, I asked them all to write reports. You know, a turning point in my career, a defining moment, exceeded my expectations. The payback for us in the United States in terms of scientific achievement has been really fabulous. The money, it's just been a really excellent investment. Shortly after NSF funded our first critical zone observatories, that $15 million to 3 different sites for 5 years, the European Commission said, this is interesting. We don't want to get behind. It's really interesting how science works on the international level. There's competition. And so the Europeans see us doing something and they don't want to get behind. And we see the Europeans do something and then we say, we better get on that. Well, the European Commission funded a program called Soil Crit Zone. They were the ones that developed that image I showed you early in this talk. I'm not going to go through all this stuff on Soil Crit Zone, but I am going to tell you really importantly, because it's important for us, is that they were directed by the European community, the funding agencies, the equivalent of our US National Science Foundation. Okay, fine, do your science. But really importantly, your science has to come back to us, the policymakers, the people who are governing, so we can make policies that'll help us learn to protect our natural resources. In this case, they were most interested in soil crit zone. Shortly after that, when we had the ARA, American Resource and Recovery Act, that Obama administration passed with the economic recovery, they funded 3 additional CZ critical zone observatories in 2009. So that brought us up to a total of 6 in the US. Once that happened, the European Commission says, we got to get on board here. And they, in 2010, funded 4 critical zone observatories. So I'll show you in a bit a map of where ours are in the United States. But in addition to the ones in the US, there's now one on the island of Crete. There's one in the Czech Republic, near the German border. There's one in Austria, and there's one in Switzerland. So here's our map. There are some smaller sites, and I don't have a pointer There are some smaller sites on here, on this map, that are not CZOs. They're what we call satellite sites. But the ones that are official critical zone observatories are the Shale Hills on the upper right in Pennsylvania, which is hosted here at Penn State. The Luquillo Forest, which is in eastern Puerto Rico, and it's now run by the University of New Hampshire. Not on there because it's buried under Panola Mountain is the Christina River Basin, which is on the Delaware-Pennsylvania border. But if any of you ever become interested in thinking about how the science from these observatories might help you in your classroom, the Christina River Basin is the one that's situated on a landscape most similar to where you live. It's on the coastal, it bounds the coastal plain and what we call the Piedmont terrain. But the coastal plain part of theirs is identical, more or less, to where you live. Then there's, I'm pointing as if you can see what I'm pointing at. There's Boulder Creek in the Rocky Mountains outside of Boulder, Colorado. There's the Southern Sierra site, which is in the Southern Sierra Nevada in California. There's the Sonoran Desert site in Arizona. And that's 6 of them. So right now, officially where we stand in the US is we have 6 sites. Yes, back there in the back.
Yeah. So where did you say?
Yep.
Where did you say the Christina River Basin was again? The border of what 2 states?
Delaware and Pennsylvania.
Oh yeah.
So the Christina River flows from just south of Philadelphia down not far from Newark, Delaware, and then ends up over in Delaware Bay. And so the upper part of it's a very large watershed. The upper part of it is in Piedmont, but the lower part of it is on the coastal plain with tidal creeks and similar environment to where you guys live.
Thanks.
We also have, associated with our Shale Hills site, we elected to establish a series of what we call satellite sites. And these are very small, not intensely instrumented like the observatories. I'll probably have to tell you about instrumentation and details of science in another time. But the reason I'm putting this map up here is that we do have a site in Virginia. It's in western Virginia, west of the Blue Ridge. Beautiful, beautiful part of your state. Has nothing to do with Portsmouth other than it's in your same state. But if you ever have interest in just bringing Virginia-related information into your classrooms, we do have a site in Virginia for which we could share information with you. Okay, soil transformations in European catchments. Just a little bit about the Europeans. Really importantly, stress. Soil trek morphed and evolved out of that thing, soil crit zone. And they, again, the European community said, okay, we're going to fund you some more, but not only do you have to help us develop policy, government policy, but you must use your funding to collaborate with partners overseas. We don't have this in the US. When I get a grant, or when any of us at a university in the US gets a funding from the federal government, we cannot spend that money on paying somebody overseas to come work with us. The European Union said, we got to stop that. I literally have gotten a month of my salary paid a year by the European Union to work with them on their project. So they recognized that, look, this has to be, just by its nature, it's international in scope. And so somehow we have to figure out ways to allow researchers to interact with each other. I'm going to skip that. I'm going to skip that and that. And then I'm just going to say that this summer, the National Science Foundation announced that they were going to fund 4 new critical zone observatories. And, well, you all know, then the federal government shut down. And so we're waiting, but what we think we're gonna be at is this map right here. So on this map in white, you can see all the sites that I already listed: Pennsylvania, Delaware, Puerto Rico, Arizona, Colorado, and California. But in addition, the 4 new sites are the Calhoun Forest in South Carolina, the Illinois River Basin in Illinois and Iowa, Reynolds Creek, which is in southern Idaho, and the Eel River in northern California on the coast. And so, you know, it's a pretty big continent, but we're starting to get enough coverage where we've got the main different geographic, eco-geologic geographic zones covered by this number of observatories. We still need some more, but we're getting pretty far along in this. I'll just mention that in addition to the Europeans and what we're doing in the US, there are a number of other countries who are getting after this in a pretty serious way. Here you can see a map in China. They've developed 23 sites in China. And as the Chinese are also capable of with their growing economy, these have all developed since the US and Europe started doing theirs. So they've quickly jumped from behind to ahead. The Australians have 2 sites. The French, the Germans have gone outside of the European Union and developed their own sites. So the French have developed them in the Caribbean, in India, and in Africa, in some of the nations that they used to have a formal presence in. So this is beginning to now become truly a global network of study sites and people. All right, so I think what I'd like to do, Dan, did you get those files I sent you?
I can check and see. I didn't as of 4:30, but I'll take a look.
Can you take a quick look?
Sure.
Does anybody have any questions? What time is it?
6 o'clock.
6. Well, here's what I'm thinking I'm going to do. I'd like to run you through just a short activity that I think you could bring